Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, construct binary tree from preorder and postorder traversal. So first, before we get into it, I want to mention this is very similar to another problem that we have solved. And yes, of course, it is a Leetcode 150 problem. So if you go to the tree section, it is this problem, construct binary tree from preorder and postorder traversal. I would recommend understanding this one before you get into today's problem. So if you look at the solution, we have pretty much like the possible solutions available here, probably in your language of choice. And I think the first solution is probably enough. And I guess the second solution as well. They are pretty similar, and they're going to be similar to today's solution. But the problem is that today's problem is actually a harder variation of the other one. So that's why I recommend solving that one first. This one is definitely harder. It's not that you can't learn anything from this problem. It's just one of those problems that, to be honest, is kind of a pain. And it's one of the problems where the constraints are kind of important. Well, I mean, they're not that important, but this one is important. The fact that all the values in here are going to be unique. They mention that here, that the values are distinct, and also that the values, mainly from this constraint and this constraint, you can tell that the values are going to be 1 through n. Of course, without any duplicates, they're going to be unique, but they're going to be 1 through n, where n is the size of the tree. So it's not a coincidence here that the values are 1 through 7. So keep that in mind. One of the reasons I think this one is harder is that there actually is possible to have multiple valid trees. So the idea behind this problem is that we are given a preorder traversal and a postorder traversal. I'll briefly mention how these traversals work, because even if you already know, it's worth walking through that and seeing how these traversals apply to this problem. I'll try to simplify it, because that's how I like to think about things, in a simple as possible way. But it's still worth walking through things in a bit more of a verbose way, especially if you're a beginner. I might not be able to do that in depth in this video, but you can do that on your own time. So the simple way to look at preorder and postorder traversal is like this. Preorder works like this, where we are processing the root, and then we process the left subtree, and I'm going to get rid of these brackets just to kind of save time or save space here. We have the root, we have the left, and the left could have multiple nodes, so I'll just put ... to indicate this. And then we have the right, which could also have multiple nodes, ... So that's how preorder works. In terms of the picture, it's like this. You do the root, then you do the entire left subtree recursively, and then the entire right subtree. So recursively, it'd look like this. Process the root once again, then left subtree recursively, and then right subtree recursively. So there's that. And then postorder is kind of the opposite. You do the entire left subtree first, ... and then the entire right subtree first, ... and then the root. So knowing this, knowing these properties, and just to kind of run through it here on the left side, postorder would be like recursively doing the entire left subtree, recursively doing the entire right subtree, and then finally doing the root. So you can see that this simplified look at it, you can see, of course, the root is going to be the first in the preorder traversal, and it's going to be the last in the postorder traversal. Now, with this, if you want to be able to solve the problem, what you have to do is try to make a few key observations about these properties and how they can allow us to reconstruct the tree. We're just given two arrays, the preorder traversal and the postorder traversal, in the form of an array, and we want to reconstruct the original tree. It's much harder than the other variation of this problem because we don't have an in-order traversal. That actually helps a lot. So I'm going to make some space here because I'm actually going to focus really on this example and using the preorder and the postorder. And we're going to use those to make those observations that are going to be important. But there's one other thing that they mentioned in the problem description. There could be multiple correct trees, and that's the thing to really keep in the back of your mind. How do you deal with that ambiguity, the fact that there could be multiple solutions? This is not enough information. No matter how many observations you make from this, it's not going to tell you the exact tree. And so the question is, how can we deal with that? How can we try to simplify it for ourselves? So here is the example. Now is time to make the observation. So here is the root. This is the pre-order, by the way, and this is the post-order. So it's simple enough if we want to create our tree to figure out what the root is. So then I have my 1 over here. And the convenient thing about pre-order traversal is this. We know that the next node is actually going to be the left child, if a left child exists. Right? I mean, that's kind of what this tells us. Over here, we have the pre-order, and then we have the left. Now, you might think, okay, well, the post-order starts with the entire left subtree as well. But the problem is that the order that the post-order traversal will go through the left subtree is in reverse order. Reverse, well, not literally reverse, but kind of in reverse order from the pre-order traversal. Let me kind of show you exactly what I mean. For the left subtree, pre-order is going to do this. It's going to say, okay, do 2. Great. And then do the left, which is 4. Great. There's nothing more to do. So then pop back up and then do the right subtree. 5. Great. So we did 2, 4, 5. Now the post order would do this. This is the post order for the left subtree, and this is the post order for the right subtree, and then this is the root. So the post order, you can see here, it went 4, 5, 2. So not literally in reverse order, but post order works bottom up, whereas pre-order works top down. Depending on the shape of the tree, these values could be in a different order. But there's one thing that is actually guaranteed. What is guaranteed? Let me show you. We saw that this was the root, and in post order, that would be over here. So let me use a different color now. We know that from this information here on the right, that the left subtree is going to be contiguous in pre-order traversal, and it's going to be contiguous in the post-order traversal. So in this case, the left subtree had 3 nodes in it. So we know that the size of this chunk is going to be 3. The size of this chunk is going to be 3 as well. We don't know that, but in this example, of course, that's true, and it's going to be true for every example. We just don't know the number is going to be 3. It could be 4, it could be 5, there could be 10 nodes in the left subtree. That number is important. And how exactly do we figure out what that number is? It'd be nice for us to be able to do that. Or in other words, it would be nice for us to be able to figure out what this boundary is. Because if we could figure out what the boundary is either in this array or in this array, then we would have enough information, because then we'd say, okay, well, we know that there's 3 nodes in this chunk, so that means there must be 3 nodes in this chunk as well. Okay, now how do you figure out that information? Which observation is going to help us figure that out? Well, I actually pretty much went through it. Remember, pre-order works top down. Post-order works bottom up. We know that 2, if there is a left child of 1, 2 is going to be that left child. We also know that wherever this 2 happens to be in the post-order array, it happens to be over here. Well, post-order says that this will be the last node traversed in the left subtree. So that tells me that this was the last node to be traversed, and thus everything that came before it also belonged to the left subtree. We don't necessarily know the positions and all that, but this is how you figure out the boundary. Let me restate it. We know that 2 was the left child, and thus if we can figure out which position, if we can perform some kind of lookup to figure out which position that value was in the post-order array, then we figured out the boundary, we figured out the distance, and this will allow us to solve the problem recursively, because now we have a chance to be able to break this down into sub-problems. Now we can somehow maybe take this chunk over here, this chunk over here, and then pass it into a recursive function where we then, instead of trying to build the entire tree, we broke it up into a sub-problem where now we are going to try to build the left subtree. And if you're paying attention, you'll probably know how to build the right subtree as well, because look what I did over here. I already said this is the root, this is the root, this is the left, this is the left. So I know that everything that's left over here in pre-order and here in post-order, that can be supplied to build the right subtree. So those are more or less the observations to make to arrive at a working solution. But there's one thing I kind of glossed over. And don't worry, I'm going to walk you through some of the implementation details for this. I think that's mostly better covered in the code anyway. But there's one very important thing that's not an implementation detail, that's more about just the solution in general, which is this. I mentioned that we know this is the root over here, and if it has a left child, the next value will be the left child. But how do we know? Like, that's where the ambiguity comes in. What if we had something like this, where let's say these values just didn't exist. Let's say these values that were in the right subtree, they just didn't exist. And so let's say that this was the tree that we were trying to build. 1, it has 2 on the left side, and then, that whole subtree. Okay, in that case, our assumption that this node was the left child, that was great. That actually did work. But what if our assumption was wrong? What if instead this entire subtree was not on the left side and it was actually on the right side? We had a 2, and then we had like a 4 as the left child, and then we had a 5 as the right child, and this is just a subtree on the right side of 1. Well, in that case, we will have built the wrong tree, but it's actually okay for us to do that, because they didn't tell us we had to build the exact correct tree. Because in this case, it's actually ambiguous. There is no correct tree. This technically follows the traversals that we were given, and the other tree also follows that as well, like if we had this. So if we don't know, then we just assume that whatever we're looking at is on the left side. And if there happens to be additional nodes, well, that's okay, because we'll have space on the right side for those nodes as well. So that's why we choose to put them on the left side. If you wanted to, you could do it the other way. You could put this on the right side. That's assuming that there weren't like 2 subtrees, but it's easier just to implement it by putting it on the left side. Because then if there are 2 subtrees, then we can put one on the left side and then one on the right side. I hope that makes sense. Now let me try to kind of walk you through a little bit of the implementation details. It's mainly going to be a matter of like manipulating the pointers. I'm not super creative, so what I'm going to say is I'm going to have, let's say, I1, which is going to be at the beginning of preorder, and I2, and then I'm going to have J1 and J2 for the other array. Conceptually, this is how it's going to work. Like, it's going to say, okay, we're trying to take this preorder and this postorder and create a tree out of them. So we know that, okay, we can take the first one in the preorder. That will be our node. That'll be the root. And now we're trying to build the subtrees. For the left subtree, we're going to say, okay, is there one more node in the preorder traversal? If there is, then we'll say that that's going to be the left child. If there weren't anything here in the first place, well, then we would just stop and we would return this node. But there is, so then we say, okay, I have my guy over here, and then I want to perform a lookup so I can figure out which index it's in the postorder array. Now, how do I perform that lookup? The easiest way would just be to dump all of these values, throw them into something like a hash map, or you could actually also use an array, because we know that the values are going to be a continuous from 1 through n, but a hash map is enough. That will tell us the index of every value, so we'll be able to look that up. We'll see that the index is over here. That tells us the boundary, so I guess I can call that like mid, but in any case, what we're going to do is take this part from J1 all the way up until mid, and then pass that in recursively to the left call. Now, how would we know how many values to get from here? Well, we could just get the distance of this. We see that there's 3 values, so then the distance from here should also be 3, and thus we can say that the boundary would be over here. And wherever that boundary is, then we can say, okay, well, everything to the right of that, all the way up until I2, is going to be passed in to the right subtree. And similarly over here, everything after the middle pointer, which is going to go there, up until but not including J2, is going to be passed in to the right subtree there. And whatever these subtrees happen to build will then be assigned to the left and right pointers of the node that we created, the root node. So is this easy? I definitely don't think so. In my humble opinion, this is actually more difficult than the problem that we solved yesterday, which was technically a Leetcode hard. That's why I don't really care too much about the difficulties that are assigned to these problems, because it's very arbitrary. Maybe some of you find this problem easier, that's fine, but I think it's very subjective. Now, the fact that our lookup is like a constant time lookup, that does mean that this solution will actually be a linear time solution, and I believe linear space because it's going to be recursive, so the recursive call stack will take up some space as well. But now I think this is enough to get into the code. And actually, I guess I could take like a few more seconds to quickly just dry run through this, or at least I'll dry run through like the left subtree, how that's going to be built. So right now we're here and we're here. So once again, we are going to take the first node that's in the preorder, that's 2. We're going to create a node here. We're going to look up where 2 happens to be, or actually, we're not going to look up 2. We're going to look at the next node, which is a 4. We're going to look up where is 4. It's over there. So that tells us the boundary, meaning that 4 is going to be passed in to the left recursive call. And since there's just a single node, that's kind of like the base case. And everything that comes after, which is just 5, is going to be passed in to the right side. And we know that that's over here. 5 is just a single number. The reason we know that we can stop here is because the distance here is 1. The distance there was also 1. And so then we're going to end up here on the left side with a tree that looks like this, 4 on the left side and 5 on the right side. So you can see that it does work. Then we pretty much ran out of values here in the left subtree. So then we would build the right subtree. It would end up pretty similar. I encourage you to walk through that if you're still unclear on how this works, or maybe wait until I code it up and then try to walk through the code. If you want to know what my thought process was, here it is, but I don't know how helpful it's going to be for you. First, I'm going to just get the length of one of these inputs. They're both going to have the same length, but then I'm going to create a hash map for them. I guess I'll call it post val to index. It'll map each value in the post order to the index of that value. And we can build it like this: in enumerate the post order array. And just for every single value, I'm just going to copy that, map the value to the index that it appears at. So now that we have that, we can implement our recursive function, which I'm going to call build. It'll take 4 pointers, I1, I2, which will tell us which portion of the preorder array that we're currently looking at, as well as J1, J2, which tell us which portion of the post order array that we're looking at. And so the way this function is going to be called, it's not really a surprise. We're just going to call build, going from 0 up until n minus 1 and 0, n minus 1. So there's many ways to like code this up, and there's many like little things you can do to simplify the code. I might do those towards the end, like the simplifications. But for now, I'm just going to kind of start with like the basic thing. What we want to do is first just create a tree node. Take the first value in preorder, which we can get with our pointer I1, and create a node out of it. Let's call this the root. Now, what if it was possible actually that the portion that we're looking at is empty? That's going to happen eventually. Like that's going to be the base case where we can't actually create a node. We can't just infinitely keep creating nodes. So I think that case could be handled like this, if like one pointer crosses the other, but I'm actually not even 100% sure if this is going to happen. I'm going to leave this as is and maybe simplify it towards the end. So that could happen, or maybe J1 could cross the other pointer. In that case, we'd want to return, and we can return null. Okay, so we created the root. This is what we want to end up returning, but we just don't know if we have to create a left and right subtree for this node. We can check that like this. If I1 is not equal to I2, then we have to create some subtrees, maybe 1, maybe 2. But either way, we need this to be true, because if I1 and I2 are equal, that means we only had one node. We already created that node, and now we can return it. So that's why we would skip this if this weren't true. But anyways, now we are going to build the left subtree. So we know that the left value is going to be this. It's going to be the next value in the preorder traversal, like this. So at I1 plus 1. Okay, now I want to get my mid pointer, what I talked about earlier, which is going to tell me the boundary in the post order traversal. And I can get that with my hash map that I created, post value to index. So I do this, post value to index. I take that left value I just computed, and let me call this mid. Okay, now using this mid pointer, I'm going to get the size of the left subtree. So I'm going to call that left size, and it's going to be mid minus J1. Because remember, mid is the pointer for the post order traversal. J1 is the beginning of the post order traversal. And so the difference will be the size, but we need to offset this with a +1. So that will be the true size. Now is the time to build the subtrees. So we will build the left subtree and then assign the result of that to root.left. How are we going to do it? Well, the starting point is going to be I1 plus 1 for the preorder traversal, I1 plus 1. And I'm not quite sure right now, like at the top of my head, what is going to be the ending of the preorder traversal. Well, I am, but I like to fill these in easiest to hardest. So we know that the postorder traversal is just going to be J1, and it's going to end at mid. So that tells us the postorder traversal part. The preorder part is going to be from I1 plus 1 up until some point, which we can get with the size, because we know that the size of this portion should be equal to the size of this portion. So we can get that by just taking I1 and adding the size to it. So I will do I1 plus left size. You might think, well, why didn't I need to do like a +1 or a -1? And that's a question I'll let you try to answer on your own, because it's literally just a math question that's not really related to trees anyway. I'm pretty sure you'll be able to figure that one out. Now we can also try to build the right subtree. So we'll do this. Root.right is going to be equal to build this. So everything else, everything to the right of this is going to be passed in to the right call. So this was the ending of the preorder portion. So we want to start one spot after that. So we can copy this and then do a +1. And then this is going to go all the way up until the end of the preorder portion, which is just I2. So I'm going to put I2 right there. And for the post-order portion, it ended at mid, so it should start at mid +1, and then it'll go all the way up until the end, but we didn't include the end, like the last element. That was pretty much what the root is, so we'll do J2 -1. That's technically correct. So I think this code is actually complete. This is the entire code. I do believe it'll work. There are some minor simplifications that we can make to it. Let me run it first. Okay, very, very sloppy bug on my part. I don't know why I had index here. It should just be I. Sorry about that. But now you can see that this code does work and it is pretty efficient. Though some minor simplifications we can make to this is, first, notice that J2, I mean, we're passing it into the recursive call, but other than that, do you see it being used anywhere here? Not really. I mean, the nodes are always going to be removed from the end of post order. We're always going to remove one node at a time from the end of it. So it actually doesn't really matter. We don't actually need this parameter J2. And so then we can probably just get rid of this part as well. And then we can just not pass J2 in there. We can not pass mid there. I think this code should work as long as I didn't mess anything else up. Of course I did. Of course I forgot to remove the parameter from the original build call. But if we remove that as well, I think this should still work. And yeah, so here you can see on the left, it does still work. I think there is one other solution to this that actually involves a little bit less code. I think it's a bit more tricky though. I thought this solution, even though it's kind of difficult to implement, once you do understand it, like it is pretty logical, it is pretty intuitive why it works. So I'll leave this as is. It's linear time, linear space. It is optimal. So if you found this helpful, check out Leetcode.io for more. Thanks for watching, and I'll see you soon.